So here I will do a brief, very brief introduction to clusters, looking at electron counting and structure rationalization. So cluster made on main group on transition metal atoms. We can call them aggregates, actually. So here will be, one more time, recipes, only recipes. If you want to learn about the demonstration, mathematical demonstration, you should go to the literature. So these have been done during the 70s, 80s, the articles. So you may have a look. It has been done and done again. So no need to do it. So I will talk on electron-deficient clusters, looking at the Wade and Mingo's electron counting rules, with few applications on these solid-state compounds containing aggregates, for example, of boron or indium or silicon here. Then I will switch at the end on the electron-precise clusters. So electron-precise cluster means that each atoms follow the octet or 18 electron rules. On two slides on this theory, polyhedral skeleton electron pairs theory, which is more general. So, okay. So, for the literature, you may read this marvelous, beautiful book written by my supervisor, actually, Jean-Yves Saillard, from Rennes University. So it's the west part of France, Bretagne. Here, and also written by Jean-François Allais, who is a research director at the CNRS at Rennes too. He was also my co-supervisor. And the third one is an American, Thomas Fellner, who worked a lot on cluster chemistry. It's a very nice, very, very nice book in English, by the way. So the Wade and Mingo's electron counting rules. So here you have two pictures of Wade. He just died 1 year ago. And Mingo's, Professor Mingo's, who was the dean of the Imperial College, actually. He switched from science to administration. Okay. So, as we did previously, we have to count the electron. We have to count. And the rules are the following. So first you have to look at the aggregate. Then you count only the valence electrons, or what we call the CEV, cluster electron count. Doesn't matter, it's the same. And for a main group aggregate, if this count follows the 4n plus 2 rule, we will have what we call a Clouseau deltahedron. Plus 4 a nido and plus 6 a arachno. I will show you what is Clouseau, nido, and arachno. Or for transition metal clusters, only made of transition metal atoms, you may have ligands around the shell, of course. The rules are 14n plus 2 plus 4 or plus 6 for Clouseau, nido, and arachno deltahedron. So the deltahedron now are coming from usual polyhedrals as the bipyramid based triangle here, or the octahedron, or this one. And when you remove one atom here, for example, I start from this one, you see, when you have one vacant site, so here, for example, the octahedron, when you have the one vacant site, you get what we call the nido cluster, okay? And when you remove two sites, you will get the arachno. So Clouseau means that all sites are occupied by atoms, nido, one vacant site, and arachno, two vacant sites, okay? So, and you have, on these rules, actually, the Wade and Mingo's rules works pretty much for most of the electron-deficient cluster that we may find.
You talk about vacant sites, so it's with respect to
these polyhedrals.
Only these 8.
I am looking at this black dot, Okay? So you may have an atom or not. When you do not have an atom, I call that a vacant site. Okay? When all sites are occupied by one atom, by atoms, it's a closo. We call that closo.
Why these polyhedrals? There is no, I don't know. Ah, okay, okay.
I don't understand. Why there is no...
Why, I mean, why they are not all possible shapes?
Cube or something.
Yeah. Oh, because when you do calculations, we saw that they follow these rules, actually. You do calculation using, for example, is what they did, actually, extended Hooke's calculations. And when you may look at their stability, their electronic structures, and after you may do a link between these rules. So for n plus x equal 2, so you have a closo shape. X equal 4, you have a nido shape. And x equal 6, you have an arachno shape. I will now illustrate. Okay, I think. Okay, so for example, let's take this compound, the well-known compound, B12H12 2-. So we count the valence electron. So we have 50 electrons here. So as you can see, you see nothing. 3 coming from each boron and 1 coming from hydrogen, plus 2 for the charge. You have 50 electrons. So as you have a main group based cluster, you should use the 4n plus x rule. So you have to determine x here. So 4n plus x equals 50. N is the number of atoms. Here is 12. So x is equal to 2. Okay? So you should have a closo skeleton for 12 atoms. You should have a closo skeleton. So what is a polyhedral with a closo skeleton? It is one. The one that I show you here in green. And actually, B12H12 2- has this structure. Okay? Do you understand? Yeah.
In this case, we never have 4n plus 6.
We may have. I will show you in 2 slides. I continue. So another case is a carborane cluster C2B9H11 2-. They have been made by chemists. So the count here is 48 if you look carefully. So 4 electrons coming from carbon, 3 coming from boron, 1 coming from hydrogen, and a charge 2-. So 48. You have only main group elements for this aggregate. So the skeleton is C2B9. It should follow the 4n plus x rule. So you determine x with n equal 11. 2 plus 9. So here x equals 4. So you should have a nido skeleton. What is the meaning of nido skeleton? You start from the closo and you remove one vertex. Is vertex, you say? And you remove one, sorry, let me show you. And you remove one atom here. So the C2B9H11 2- has this structure, actually, a nido one, what we call a nest-like structure. Icosahedron with one vacancy. And the vacancy is always the one which has the more coordination, the highest coordination, the highest atoms around. Okay? So third case, B10H14 2-. So here the cluster electron count is 46. So x is equal to 6 because you have only 10 atoms here. So you should get an arachno skeleton. Okay, because x equals 6. An arachno skeleton coming from 10 plus 2 vacant, so from a polyhedral with 12 vertices. So the structure is a cobweb like this. It looks like this. By the way, I show here only the boron atoms. You have hydrogen, of course, in the periphery. You may have hydrogen as a terminal hydrogen or as a bridge or maybe in a ternary site. These rules do not say anything about the position of the ligands. We are only talking on the skeleton of your cluster, or to rationalize the skeleton of the cluster. Okay? So let's take now a solid state compound. So calcium B6, a well-known calcium B6. So if you look carefully, so of course you have calcium atoms. So if you use the Zinto-Clem concept, you should have Ca2+ formally. So you will have B6 2-. Look carefully here, you see you have octahedron B6 in this network. B6 octahedron. So we have to count the electron. B6, so you have 18. The charge coming from calcium 2. And each octahedron is linked to 6 actually octahedrons. 4 in the main plane here, and 1 above and 1 below. And you may describe this bond as a 2-center, 2-electron bonds. It's a single bond. So you have 6 times 1, because each, you see, each B6 counts for 1 electron. So you have 6 electrons here. So the cluster valence electron, or the count, is 26. So for 26, for a main group aggregate, you have to use the 4n plus x rule. Here, n is equal to 6. So x is equal to 2. So you should have a Closed skeleton for B6. And the Closed skeleton for B6 is an octahedron. That's it. So you may rationalize why in calcium B6 you find such octahedron.
It's not clear about last 6 electrons.
Okay. So here you have a 3-dimensional boron network. Okay, it's a 3-dimensional boron network. So if you look at this B6, how many B6 do you have around? 6. Okay? And so 6 which are linked through sigma boron-boron bond. Okay? So if they are linked through sigma boron bond, it's a 2-center, 2-electron bonds like this. You see that this octahedron here, B6, counts for 1 electron. We have 6 around, so 6 times 1, 6. Okay? So it's why we get 26 electrons here. So you may understand, using the Wade rule, why you have a Closed skeleton in this solid state structure. So another case, a little bit more complicated, but it's just to illustrate that how powerful are these rules. So here is cesium, indium 3, CsIn3 here. So you see that in yellow the cesium atoms, and in red the indium ones. So what type of structure do we have? So first you have an indium here which is 4 coordinated, as you can see, 1, 2, 3 and 4, forming a tetrahedron. Okay? So formally you may assign a minus charge to indium. As you can see here, is my choice. CS3In9, so you will get 3 CS plus In minus plus formally In8 2 minus. So this one is In minus. So this atom, or let's say anion, has the same number of electrons than carbon. So the VCPR theory says that this fragment is AX4E0. So you should have a tetrahedral around each indium. for this case, okay? So you may understand why you have this geometry, these local geometries, sorry. So here is the first indium, crystallographic indium site. And the second one is this cluster, you see, in green here, which looks like this. Is what we call a bis-dis phenoid cluster, made of 8 indium atoms, formally with a charge of 2 minus. Formally, with a charge of 2 minus. So why we have such geometry? So you have to count the electrons, the valence electrons. So for IN8 you have 24 electrons, 3 per indium. You have a charge of 2. And here, what's again, if you look at the structure, you see that, you have 2 center, 2 electron bonds here, 1, 2, 3, and 4. So you have this cluster which is linked to 4 In minus, so 4 times 1 here, and you have also this connection. So one cluster with another cluster here, and here, and above. No, just here, sorry, in this plane. One cluster here, and another cluster here, through 2 single bonds. You see? So you have 4 2 center, 2 electron bonds. So you may count 4 electrons. So the total is 34. So using the Wade rule, x is equal to 2. So you should find for IN8, 2 minus, a closed skeleton. A closed skeleton for 8 atoms. Okay? So let's have a look at the previous slides. So this one. So for 8 atoms, so 5, 6, 7, 8, is this one. Is the one that I showed you here. This one. So you may understand why we find this cluster in CSIN3, actually. So, okay? Maybe okay. So another case. So it's one phase of boron, the alpha B12 structure. So the alpha B12 structure is made of icosahedrons, as you can see here. So here is alpha B12. So you have to apply this formula, but let's count first the electron. So you have 36 electrons coming from B12, 3 times 12. Perfect. You have 6 electrons coming from the terminal bonds. If you look carefully here, each icosahedron is linked through to 6 icosahedrons. So here it counts for 6 electrons. And here you have plus 8 electrons, because you have 6 3 center 2 electron bonds. This one here in the structure. You see, you have only 2 electrons here between 3 icosahedrons. Only 2 electrons for 3 contacts, let's say. As we have seen in H3+, actually. So the total number in this case is 50 electrons, as we can expect for a closed skeleton. X is equal to 2. So for this number of atoms, a cluster with 12 atoms, as a closed, it should have the icosahedron structure. And one more case. So one more case is a solid state compound with block S element, potassium. You have 12 potassium, and silicon 17. So here is very complicated. It could be very complicated unit cell. So you may do what you want. You're using your techniques, DFT calculations, bond structure, or whatever. But here you may explain why you have such a tetrahedron here in yellow, and this red cluster here, which look like this one. Okay. So formally, key 12 silicon 17 may be divided in two clusters. The first one could be silicon 4 minus. I assign a charge of 4 minus for this cluster. So which is isoelectronic to phosphorus 4. Phosphorus 4, P4. So here we have 16 electrons coming from silicon, a charge of 4. So the number of valence electron here is 20. You apply the weight rule, so you have X which must be equal to 4. So you should find a nido skeleton. Okay? A nido skeleton. So if you have a nido skeleton, it means that the polyhedral it's 4 plus 1 vacant polyhedral. So based on 5, with 5 atoms in your structure. Okay? 5 atoms, it's a bipyramid triangular based. A triangle based bipyramidal. Okay? And you remove 1 atoms. So you have a tetrahedron. Yeah, are you following me?
Yes.
No? Not quite? It's okay? You start, I can draw maybe. Like this. So the polyhedral is 4 plus 1, 5 is this one. And as this cluster is a nido, is of a nido type, 1 atom is removed. Okay? You remove 1 to get the nido. So what do you get? It's a tetrahedron. This one with silicon, 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 silicon. So you may understand why you have such aggregates in this compound. There is another way to get this, because P4, so this one is isoelectronic to P4, and I can do here, it's an electron precise cluster. I can draw a Lewis structure. Each silicon has 4 electrons, right? Plus 1 electron coming from the charge, because you have 4 silicon. So you have 5 electrons around each silicon. Okay? 1, 2, 3. So 5, you should have a lone pair on silicon. So each silicon is AX3E1 type using VCPR. So the steric number is 4. So coming from a tetrahedral, but without 1 side. So you should get something like this, as in NH3 is what we have here. And this is what we have in P4, actually. Elemental phosphorus, one phase contains only P4 units, P4 tetrahedral units. You may check that. Okay, so I rationalize this cluster. So with 4 minus electrons. So let's go to this one, the silicon 9 4 minus. So which looks like this. So why? Silicon 9. So you have 36 electrons, a charge of 4, so 40, a count of 40 electrons. So if you use the weight rule, you should get X equal 4. So you should have a nido skeleton, okay? You should have a nido skeleton. So the polyhedral, let's say the father or the mother, I don't care, contains 9 plus 1 atoms, okay? So 10. And for 10, you see the 10th one is here. And I remove it and I got this polyhedral. You have to look at the, the representation of the father, let's say, or mother polyhedral. As I wrote here, the parent polyhedra is n plus 1, so 10 is a bicapped, I think, square antiprism. And you remove one side, zoom, and you get this cluster. So you may rationalize this structure, and you may understand why such structures, such aggregates, exist in this K12 silicon 17 solid state compound. Question here? Nothing to say. Okay. One more. So KSN. So with tin.
And what about potassium?
Oh, but potassium is happy. Potassium is a block S. It gives one electron, so it follows the octet rule. Potassium has only one valence electron. And I consider that when you have the mixing of a block S element with a main group elements, you have a charge transfer from the block S to the main group units. Okay? Is what I did before, using the Zintal claim concept. It's a rule. In solid state, I say. Okay? So when I say block S, I mean all the elements except hydrogen and beryllium. But, so alkaline and earth. Alkaline, you say? Or alkyne earth? Well, you see. The first group and second group. Okay? So this one, KSN. So KSN, one more time. You may think that this solid state compound is made of 4 K plus. So K plus is happy, octet rule. And SN4, 4 minus. So you have 14 atoms in your cluster. So you count the electron, 2. So SN is the column of carbon. So you have 4, there is 4 valence electrons for tin. So 16 for SN4, a charge of 4. So you have an electron count of 20. And in this case, you may use the Wade rule. Let's say that you use the Wade and Mingo's rule. 4n plus x. So x should be equal to 4. So when you have x equal to 4, you have a nido, a skeleton. So the father is 4 plus 1. Okay, this one. And the nido is also this one. But you may use also what we call the electron-precise cluster count, the 5n rule. 5 times 4 equals 20. Electron-precise means that each atoms follow the octet rule, as you can see here. Of course, the two theory-based rules go to the same conclusion. Go to the same conclusion. And as I said previously, you may use also VSEPR, but only looking at the local environment at each atom. And you see that the tin is AX3E1. So the steric number is 4, so you should have a tetrahedra without one side. So the local geometry is a trigonal pyramidal, as in P4, or as in silicon 4, 4 minus, which is isoelectronic to SN4, 4 minus. So here we can understand also why we get such clusters encapsulated in potassium network. What else? Oh, the last one. So the last one is molybdenum chlorine 2. It's a layered compound containing metal clusters. If you look carefully here, you have octahedrons here, linked through a chlorine bridge. So why we have such a structure on such stoichiometry? So we may focus on the cluster here, one unit only, and you have to see here that you have an octahedron of 6 molybdenum atoms in black, bold black here. You have an octahedron. And you have 3 types of chlorine atoms. Terminal chlorine, as here, just on the top of the octahedron, in front of the slides here, let's say, on the below. You have also this type of chlorine coordination, what we call the mu Cl. You remember, mu means that Cl bridge two molybdenum atoms in this case. And the last one is mu 3 Cl. So Cl sits in a ternary site on a triangular. You see here, you have a triangle here, sorry, and you put above the triangle a chlorine atom. So it's a mu 3 atom. Okay? So you may write this cluster as MO6, mu 3 Cl8, mu Cl4. You divide by 2 because this chlorine is shared by two clusters. Mu Cl2 divide by 1 because it's a terminal chlorine. Okay? So let's count now the electron. So MO6, so you have 36 electrons, 6 valence electrons per molybdenum atom. So mu 3 Cl, so how many electrons? So mu system, so you have to draw mu 3 Cl. So I do it. I can draw like this. Mu 3 Cl. How many lone pairs are you going to put here? Oh, no, let's say again. Sorry. Cl has 7 electrons. Where do you put the electrons here? Huh? Where do you...
We count each of that bond as two bonds, two electrons.
If you want. Yes. No, bon, I answer. You have one pair here, another here, one electron here, and a lone pair here. As in this local coordination. You have 7 electrons, okay? So mu 3 Cl counts for how many electrons? How many electrons it give? It give 5. Okay, mu 3 Cl. It's a 5 electron donor. It's a 5 electron ligand. When is mu 3? When is mu 3? You may look at your notes. I've wrote in your table this result. Okay. So let's switch to mu Cl now. Mu Cl. So Cl in bridge. Okay. So here, what you can do, you can put a lone pair here, formally. 1 electron here, and 2 here. So mu Cl will give 3 electrons in this case. And the terminal Cl, of course, will give 1. Each will give 1 electron. This one. Okay. So depending on the coordination mode, a chlorine atom may give 5 or 3 or 1 electrons. Formally, of course, formally. After everything is delocalized, but it's a way to count. This is the way that we use in chemistry. So mu 3 Cl8, so you have 5 times 8. Mu Cl4 divided by 2, so 3 times 4 divided by 2. On the terminal chlorine atoms, or chlorine terminal ligand, count for 1 electron by 2, because you have 2. 1 here and another here. Okay? So the total number is 84. On 84, if you look carefully, it's an electron-precise count. Because how many bonds do you have? How many metal-metal bonds do you have in an octahedron? 12. You have 12. So you need for 12 bonds, you need 24 electrons, right? If you consider that you have a 2-electron, 2-center bonds. Is what I mean by electron precise. You should have a 2-center, 2-electron bonds. So here 18 is coming from the 18 electron rule times 6, okay, minus the number of total valence electron, so which is to 24. So here you have 12 2-electron, 2-center metal-metal bonds in this cluster. It's an electron-precise cluster for this case in MoCl2. Yes?
a related question. To move 3Cl,
Move
Which-
this, yeah.
which oxidation state would you assign to this chlorine? I'm a bit puzzled.
Oh yes, 1.
Why one?
But because here you have a lone pair, here you have a lone pair, and here you have only 1 electron. What is the oxidation state for here? For a terminal chlorine?
0, as long as when it
No. When you no, not 0. When you count when you determine the number, the oxidation number is within a molecule.
Okay, then
Always
it's
is -1 as here.
because the lone pairs are coming from chlorine, so
The lone pair here, if you want, we can write this ligand as a L2X ligand. This one as a LX. Oh, sorry.
okay.
LX ligand, and this one is a X ligand. You remember? So when you look at the ionic model, each X wants to be L, so it takes 1 electron from the metal center. So here 1, and here 1. Okay? For this oxidation number. Okay, so now I will finish with this another way of counting the electron, because you see that up to now we can rationalize using the Wade and Mingo's rules only for clusters made of main group elements or transition metal elements. But sometimes you have a mixing in cluster chemistry. You may have main group and transition metal elements in the same cluster. So there is another theory. So it's a polyhedral skeleton electron pair theory here, PSEP. And for this time, in this theory, or let's say the rule, you will count only the electron within the cluster, not the electrons that you need to describe, for example, the metal ligand bond, as we did here. You have to recall that, for example, here, in this case, we count also this bond, okay, for 84. We add also this bond on the other bonds, actually, all of them. So the electrons for the metal ligand bonds and also the metal bonds. For PSEP, we will look only at the bonds within the cluster. Let's say that you have, how do you say, nude clusters. So you remove the ligands. You take only the cluster. For example, here, we can remove the ligands and we will have only MO6. Anyway, on these times, the rules are, so for Clouseau, is what we call N+1, or Nido N+2, Aragno N+3, and you can go down. The last one, but is pretty rare, is a I4 skeleton, N+4. So with 3 vacancies. So I'm going to illustrate now. So I do again this cluster. You remember C2B9H11 2-. First, I count the total number of electrons. So the total number of electrons is 48. We did already that, okay? 48. After, you count the number of electrons for each BH and CH unit. Each BH and CH unit. You have formally 11 CH or BH unit, as you can see here. You consider that. And you consider that each bond is described by 2 electrons. By 2 electrons. So you have 11 times 2, so 22 electrons. To describe the bonding between boron and carbon and the ligands. The ligands here are hydrogen, but it could be phosphine or other things, doesn't matter, or chlorine. So the number of skeletal electrons is 48 minus 20. I count here the number of electrons only for the nude cluster, okay, the skeleton. Here is skeletal, maybe. So you get 26 electrons. Then you divide by 2 in order to get the pair of electrons. The skeletal electron pairs. So you have 13. Okay? So 13, you use this rule, n plus x. So n is here is 11. You have 11 main group atoms. Thus, x is equal to 2. When you have 2, you have so I did a mistake here. Yes. When you have 2, you have a nido compound. Okay? So you should get a nido structure. Thus, if you have the nido structure, the tetrahedral parent, father mother, is a icosahedron with 12 vertices. So therefore, C2B9H11 2- is a cobweb-like structure based on an icosahedral with one apexis missing, the one below. So it's another way. But this theory is more general. You may apply it for a cluster mixed with a main group and transition metal elements. Okay. So it's the last one. Last slide. So do you have questions? Or it's just recipes?
Okay.
Go back?
Yes, and no.
From where?
Can you repeat how to calculate number of electrons for each BH station?
How to calculate the skeleton electron pair here? No. Here?
Yeah.
Yes. We consider here that the ligand, so in the sphere, on the sphere made by C2B9, this ligand is connected to boron through a 2-electron 2-center bond. It's my hypothesis. Okay? Outside the cluster, the metal or main group ligand bonds are described by a 2-center 2-electron bonding. Okay? So we need 2 electrons, right? For one BH unit. And the same for a CH unit. Okay? How many CH or BH units do you have in these clusters? We have 11. So 11 times 2, 22 here. So after I go to 48 minus this number, so I get only the electrons to describe the bonding in the nude aggregate made of boron and carbon. So we got 13 pairs of skeletal electrons. It's another way. Actually, we use this one. It's more general because you can look at, as I told you, mixed clusters with transition metal as cobalt, for example, with carbon or phosphorus or whatever. And it works pretty well. Oh, of course, you have exceptions. When you have rules, you have exceptions. Okay. So it's a brief introduction to cluster counting.